3.3 Derivatives of exponential and inverse trig functions. Exciting. So this first example shows a function and its inverse. So we've got a function over here and we've got its inverse reflected across the line y equals x, just like any inverse is. One of the things we're going to learn today is if you take a look at the slope of the tangent line at 0.21, you'll notice that the slope is 3/4. If you look at the inverse function at 1, 2, which is right where you switch x and y, our slope is 1 over that, which is 4/3. Moral of the story is a formula that you're probably not going to memorize long term, but it's a formula that you might need on the AP test when you get to a specific table. Most of the time we can find the inverse ourselves and do something with it, but in those cases that we can't, we have to use this formula, which basically says the derivative of the inverse function at a value of x is the same thing as the reciprocal of the derivative of the original function at the y value. Confusing, but as we are preparing for the AP test, we'll talk more about this formula later. Next up, part of the meat of this lesson is this theorem. It says, suppose we've got a function and the slope of this function is always positive. You should be able to look at that and understand that means always positive or always negative. Another way of saying that, the function is always increasing or the function is always decreasing. No, that wasn't really always decreasing. Always decreasing. If that happens, then the function is 1-to-1. We know what that means from pre-cal. 1-to-1 means that the function passes the horizontal line test, which means its inverse is a function. If this happens, then the inverse is differentiable at all values of x in the range of f, and the derivative is given by the formula on the previous page. So let's take a look at this in practice. Example says, consider the function f of x equals x to the fifth plus x plus 1. Part A says, show that the function is 1-to-1 everywhere. If it's 1-to-1, that means the slope has to either be positive or negative everywhere. If we're talking about the slope or the derivative or the rate of change, we need to actually find the derivative, which is easy enough in this case. You should be able to convince yourself why this is always positive. Anything to the fourth is either 0 or positive. Times 5, still 0 or positive. Plus 1, now we're guaranteed to be positive. So this slope is always positive everywhere. Since that happened, then the function is 1-to-1. That's what we wanted to do on part A. Part B says find a formula for the derivative of f inverse. If we're going to do that, we first need to write the inverse function, which means switch our x and y's. Since we're trying to find a formula for the derivative, we need to find dy dx, which means we're taking the derivative with respect to x. So we're going to use implicit differentiation. This should look familiar from back in 3.1. We've got to get that dy dx by itself, so I'm going to factor out a dy dx. Left with 5y to the fourth plus 1. One more step, I divide, and I get dy dx. I can't really get this in terms of x necessarily, but I can get a formula for dy dx. Part C asks me for f inverse of 1's derivative. we think about what this really means, that means I want the derivative at the point on this inverse where x equals 1. And if x equals 1, a quick check could show us that y equals 0. If you're not sure how I get y equals 0 from that, plug in the x and solve for y. It's not something you can solve algebraically, but it's a trivial solution. Notice that you plug in 0, you get 1 equals 1. Now I can plug in my x and my y from this equation. My y is 0, my x is 1. Notice there's not even an x in this formula, so I just plug in my y value. 5 times 0 is 0. So my slope at x equals 1 is 1. Done. Alright, next up we've got some derivatives of exponential functions. This is the one you actually have to memorize, because if you memorize it, you get this one for free. Let's talk about why. We're told that the derivative of b to the x is always b to the x times the natural log of b. Let's apply that to e to the x. If I want the derivative of that, I would say, first I rewrite b to the x, which in this case is e to the x, times natural log of e. All together now, what's the natural log of e? Good job, 1. E to the x times 1 is just e to the x. So we just found our first interesting case where the derivative of something is itself. I can only think of one other time when that happens. See if you can figure it out too. There's one other time when something is its own derivative. That being said, let's try a few of these. The derivative of 2 to the x would be 2 to the x times the natural log of 2. Done. E to the negative 2x. Rewrite e to the negative 2x. We don't have to write natural log of e because natural log of e is 1. We do have to use the chain rule though, because that negative 2x is a mess. I have to multiply by the derivative of negative 2x, which is not negative 2x. Negative 2. Simplify that a little to negative 2e to the negative 2x. Done. Next up we've got e to the x cubed. So first we rewrite e to the x cubed, then we use our chain rule, derivative of the mess. And we can make that look a little nicer. Done. And last up, e to the cosine x. Again, we just rewrite e to the cosine x times the derivative of cosine x. Clean that up a little bit. Done. Finding derivative of e to something is going to be much more common than any other base. Like that first example that has 2 to the x, we won't see that very often. E is definitely the base of choice in calculus. Okay, now we have the crazy problem. It says use logarithmic differentiation to find the derivative of this. We have not ever found the derivative of something to something power where there's an x in both. This is kind of a higher level problem, and the way we're going to do it is implicit differentiation. Let's talk about what I mean by that. This problem scared me for a second. I knew we were going to have to use a log in this, and I was thinking we didn't know how to find the derivative of a log yet. Silly me, I forgot Miss Collins recorded that video. So let's take a look at this function. We don't have a rule that says we can drop down. We can't use the rule exponential rule because that only works if this base is a number, like 2 or e. We can't use the power rule because that only works if the exponent is a number like 2 or 3 or 7. So none of the rules we know are going to work in this problem. So we have to use some math magic. We have to rewrite this in such a way that we do not have a base and an exponent that have x in them. And one way that we learned how to get rid of an exponent that we don't like is using logs. Before I attack this problem, let's take a trip down memory lane. back in the old days of Algebra 2, we solved problems like this. And we didn't like having x as the exponent. So what we did was we took log of both sides. Any log we want. I'll do natural log because I like natural log. So I'm going to take natural log of both sides, and hopefully remember that meant we could drop down the x. Now I have natural log of 3 equals x natural log of 4, so x equals natural log of 3 over natural log of 4. That's how we handled exponents that we didn't like in Algebra 2. Well, good news. We're doing that again. We're going to take natural log of both sides. So we'll take natural log of one side, natural log of the other side. And just like we did in Algebra 2, we get to take that exponent and move it down. So we end up with natural log of y equals sine of x times natural log of x squared plus 1. And lo and behold, we now have something we know how to find the derivative of, hopefully. I see that we're going to have to use implicit differentiation because we don't have y by itself. I also see that we have a product rule. Going through the motions, derivative of natural log of y would be 1 over y times dy dx equals, now we have to use the product rule, which is, of course, gf prime plus fg prime. Take the second function times the derivative of the first plus the first function times the derivative of the second. Derivative of natural log of something would be 1 over that something times derivative of the inside. That's the chain rule piece. So we've got kind of a mess, but we can clean this up a little bit. Natural log of x squared plus 1 cosine x plus 2x sine x over x squared plus 1 equals 1 over y dy dx. One more step kind of finishes us up. We can multiply both sides by y. Then we get dy dx equals natural log of x squared plus 1 cosine x plus the other fraction all times y. Normally we'd stop there. We're okay with having x's and y's in our answer. But in cases where we can avoid it, why not? We know what y equals. If you look back at the original problem, we know that y is x squared plus 1 raised to the sine x power. So instead of putting a y here, we could put a, x squared plus 1 to the sine x power. And leave all that other stuff the same. Natural log of x squared plus 1 cosine x plus the fraction, all in parentheses, equals dy dx or y prime. We can even say f prime of x, because now everything's in terms of x. And that's it. That's our crazy problem for today. Unfortunately, now that we're done with the crazy part, we have the annoying part. Got 6 more formulas for you. Formulas that I don't necessarily expect you to memorize overnight, but definitely know where to find them, and keep in mind that you're going to have to know them eventually. I'd say the most important ones would be, sine, cosine, and tangent inverse. These are the derivatives of the inverse trig functions. So you're going to have to reference these, memorize them. Notice they all kind of look the same. Derivative of inverse sine, inverse cosine look exactly the same except for the minus sign. Same thing with inverse tangent and inverse cotangent. They look exactly the same except for the minus sign. And the same thing for inverse secant and inverse cosecant. So it's not really that many different things you have to memorize, but you do have to know these. I'd say start off with the first 3 that I have checked here and move on from there. That being said, our next example is going to use inverse sine and inverse secant, so we need to know both of those, or at least be able to use them. So example 5 says, find the derivative of these guys, and hopefully you can notice that there is a chain rule built into both. So let's apply our formula on part A. The derivative of an inverse sine was 1 over the square root of 1 minus whatever was on the inside squared. So if I want to square, instead of saying x squared, I'm going to say x cubed squared, which is x to the 6th, times whatever the mess was, the chain rule piece, 3x squared. So I'll clean that up a little bit. We get 3x squared over square root of 1 minus x to the 6th. Done. Part B, we have to use our inverse secant formula, which tells us to find this derivative. We're going to say 1 over absolute value of whatever's on the inside, absolute value of e to the x, time out. I want to go down a trip on memory lane again. Absolute value of e to the x. Pause the video and convince yourself why we don't need the absolute value signs. 3 seconds, I'm going to tell you why. E to any power is never negative. Think of the graph of e to the x. When is this negative? You got it. Never. So absolute value of e to the x is the same as e to the x because e to the x is always positive. Sometimes that's not the case in these problems. In this particular case, e to the x is always positive, so I don't need the absolute value sign. In my square root, I'm going to go u squared. In this case, u is e to the x. E to the x squared is e to the 2x. So e to the 2x minus 1 times the derivative of the inside. E to the x is our favorite derivative because the derivative of e to the x is e to the x. Some beautiful things happen. E to the x cancels out. We're left with 1 over square root of e to the 2x minus 1. Done. Do not blow over the quick check exercises. Do them, try them, come in ready to be excellent. Have a wonderful day.